Good day. Recently I did a video on the complete initial setup for an Arducopter FPV drone. If you missed it, make sure to check it out through the link in this video's description below. This is the second video in our ArduPilot, specifically Arducopter playlist series. Today I'm going to demonstrate the Arducopter tuning process I went through for my 4-inch prop Arducopter build, and that's described on the ArduPilot.org site. We'll start with a general basic initial tune, then use the ArduPilot Autotune feature to refine the PID values, and finish by tweaking the Arducopter Autotune to get it locked in for Acro, stabilized, and GPS-assisted flight modes. It's Arducopter Tuning Time!
Why do we need to do any tuning at all? Well, that's because our quadcopter doesn't really fly exactly how we command it. There's a difference between what you command it to do and what it actually does. That difference is called error, and we want to minimize that error as much as possible. We can do that by adjusting our P, I, and D gains of our PID controller. This little diagram down here shows a basic PID controller and what the P, I, and D terms generally do. So here's the basic Arducopter tuning process we'll be going through. First, we're going to start with the default PIDs that are provided in Mission Planner for 10-inch quads. Then we're going to do a little magic with our keyboard by pressing Alt-A. We'll adjust some parameters and conduct a hover test flight to see if we have any noticeable significant oscillations. If so, we'll adjust our PIDs if necessary. Then we'll conduct an altitude hold test flight because we'll use that for our auto-tune, and again adjust any parameters if necessary. Then before we do our auto-tune, we're going to do one last test flight to see if our quad is able to self-level, because that's going to be important also for our auto-tune. Then we'll use the ArduPilot Autotune feature, which will automatically adjust our stabilized P term and also our rate P and D terms, along with our rotational accelerations. Autotune could result in a tune you're happy with. However, more than likely, you're going to want to tweak a few of the values. So I'll go over a few of the tools in Mission Planner I used to manually tweak those values and come up with my final tune. As I mentioned, we'll start with the default PIDs. So let's go ahead and take a look at those. With our quad connected to the computer through a USB cable, we go to Mission Planner, Configurator, Extended Tuning. These are the default PIDs and other values loaded into our Arducopter firmware. These are designed for a 10-inch quad, specifically the 3DR Iris. These may work well enough for you to perform an autotune, depending upon the size of your Arducopter. However, before jumping straight into an autotune, I'd highly recommend performing those other preliminary pre-autotune steps we just talked about, and I'll demonstrate here shortly. Since we're using a 4-inch Arducopter for this video, I know I'm most likely going to have to change the PIDs from these 10-inch defaults. So what I've done for you is create this chart of example basic initial PIDs for Arducopters of different prop sizes, which should be a good starting point for an autotune. Of course, we'll still need to go through the pre-autotune steps we mentioned earlier to verify that they work. I also want to point out there's a reason that these values are highlighted in purple. If we go to our next step, we also have Mission Planner keyboard Alt-A highlighted in purple. That's because when we connect our quad to Mission Planner, go to the Data tab, and on our keyboard press Alt-A, we get a pop-up window for a plugin designed by Andres Schaffer. This little widget asks you a few questions about your prop size, battery cell count, max and min voltages. With that information, it automatically produces those values we saw earlier, highlighted in purple. Then all you have to do is click on the right button instead of searching for the parameter in the full parameter list and changing the values there. It's a real time saver. In fact, it updates more than just those values we saw highlighted in purple earlier. It also updates these we see on our next step, and some others we'll see later on. This Alt-A plugin is currently being incorporated into the mandatory hardware setup section for the latest beta release of Mission Planner. So in the future, you won't even need to do Alt-A anymore. It'll be part of the initial setup process. So now that we've updated some of our parameters using the Alt-A plugin, we still need to update some other values on our example PIDs chart not highlighted in purple. To do that, we go to our Extended Tuning tab in Mission Planner, change the values here, and then write the parameters. Our next step is to conduct a motor spin test to determine our motor spin arm and motor spin min values. So let's go to Mission Planner, Setup, Optional Hardware, Motor Test. With your props off and the quad connected to Mission Planner through your computer, we're going to see the minimum throttle percent needed to spin the motors cleanly when the quad is armed just by changing these percent values up here. Usually it'll be about 4 to 5%. You may want to bump it up just a little bit since the motors aren't spinning any props during this test. So we'll start at 5% and test motor A. And that spins fine at 5%. What if we dropped it down to 2%? That works at 2%. What about motor B? Not so much. So we need more than 2%. Let's make it 3. 3 works for motor B. Works for motor C. And it works also for motor D. So it looks like our motor spin arm throttle percent that spins the motors cleanly could be 3%. But once again, we may want to bump it up just a little bit since during this test it's not spinning any props. So 3 to 4% should be good for our motor spin arm. Then once we determine that, we can set motor spin min thrust percent high enough to spin the motors with a minimal amount of thrust applied. This is going to be a higher value than your motor spin arm and should be between motor spin arm and about 0.3. For our 4-inch Arducopter, I've determined through test flights that 0.185 is the best value for its flight performance. Our next 3 steps consist of changing or verifying some parameters before we do our first test hover flight. Fortunately for us, the ones highlighted in purple have already been done through the Alt-A plugin we used earlier. The ones in black text are default values, which we're not going to change. So the only ones we need to do anything with are these parameters in blue text. First, we'll quickly look at these 5 using the Mission Planner full parameter list search bar with our Arducopter connected to Mission Planner. We just need to type in the first few characters of the parameter and it'll show up like that. Change the values and click Write Parameters. We'll do the same for motor thrust hover, where 0.20 was the default for our Alt-A plugin. I'm going to change that to 0.15 for our 4-inch Arducopter. By the way, this range of options is not hard and fast. These are what's highly recommended. However, you can go outside of these if you so desire. Yes. Yes. And then the last 3 with motor spin, I've already made the changes. While we're here in the full parameter list, we'll go ahead and do the Acro yaw P and verify that that is set to 3.6, which is what we want. It doesn't hurt to write parameters. And now we'll change these other parameters by going to our Mission Planner Configuration Extended Tuning tab and fill in our INS gyro of 80. And then these 45.5s end up being 40, and our yaw FLTE is default of 2. So we just change these 45.5s to 40, which is half of our INS gyro frequency. And then we click Write Parameters, and let's go ahead and refresh them just to make sure that they've taken. And we see that our changes have been saved. Now it's time for our first test flight with our ATC throttle mix man set to 0.1, and we can verify that through our full parameter list that we were just in. We'll take her outside, take off in stabilized mode to an altitude of about 1 meter, and perform some small roll and pitch movements to look for any significant oscillations. If we don't have any, we can go on to our altitude hold test flight. If we do see significant oscillations, will reduce our roll and pitch PID parameters through the extended tuning tab by 50% from their current value and re-accomplish the hover test flight until we don't have any significant oscillations.
All right, this is our hover test. I'm going to switch into stabilize mode. Then I'm going to launch and gain altitude to about 1 meter. And we're going to check to see if we can hear or see any oscillations when we do some small pitch and roll maneuvers. Sounds real smooth. Pitch maneuvers, roll maneuvers. And I don't hear or see any oscillations. That's a good sign. That tells me we're ready for our altitude hold test. Nice.
All right, as I just mentioned, since we didn't observe any oscillations, we're ready to proceed to our altitude hold test. For our altitude hold test, we're going to need to set this parameter mote hover learn equals 2. That's right, ArduPilot, specifically Arducopter, has the ability to learn your throttle hover value, which is pretty amazing stuff, I think. We'll take off in stabilize mode to about 5 meters in altitude, switch to altitude hold, hover for about 30 seconds, land and disarm, and then we'll come back and set these two parameters also. If during this test flight we have oscillations vertically, then we'll reduce these values by 50% from what they were originally. In order to set any of these parameters, we go once again to our Mission Planner config full parameter list. Let's go ahead and do that now. All right, since we've done this a few times before, we already know how to do this. We go to Mission Planner, config, full parameter list, search bar, mote underline hover, and it should come up, and it does, and we set this to 2, which is learn and save. Then we hit write parameters. Yes. Outstanding. Time for our altitude hold test.
All right, I'm going to launch in stability mode, get to an altitude of about 3 or 4 meters. It won't be 5. I'll switch it into altitude hold mode, and you should be able to see the altitude in the lower left-hand corner of the goggles DVR video. I'll hover for about 30 seconds or so, come in and land, and then we'll switch the parameters inside that we talked about earlier. I'm going to put my goggles on with my fat strap goggle strap. Hold this up, do pretty good, about 3 meters. Nice. Bring her in.
All right, we just completed our successful altitude hold test flight, and I didn't notice our Arducopter oscillating up and down at all, so we're not going to need to reduce these parameters by 50%. What we will do is go ahead and set these PSC underline ACCZ parameters by going to the full parameter list. We'll change the A to 2 times the motor thrust hover, and we'll change the P equal to the motor thrust hover. That means we need to go and check out what the motor thrust hover is. Let's go ahead and do that. So here we are in Mission Planner, config, full parameter list. Motor thrust hover is 0.125. which is outside the normal range of 0.2 to 0.8, but that's no issue for us. Remember what I said earlier, that this range of options isn't hard and fast. So we'll take 0.125 as our motor thrust hover and change PSC underline ACCZ P to that value, 0.125. And then we want to change I to 2 times that value, which is 0.250. And we'll write our parameters. And I'm going to refresh the parameters to make sure that they save properly. And we see that our I term is 0.250 and our P term is 0.125, which is our motor thrust hover value. So we're good to go, which means we go to our next and final test flight before our auto-tune, as long as we don't see any big overshoots or oscillations. And in this test flight, what we're going to do is test the Arducopter's capability to self-level after we've provided it with some larger roll and pitch inputs. We want it to be able to spring back to its center position and self-level without any big overshoots or oscillations. If we have any, we're going to stop right away and make some changes. As long as we don't, then we're ready to proceed to our auto-tune. So let's go ahead and check out its self-leveling capability in our next test flight.
All right, now we're ready for our self-level test flight. I'm going to take off in stability mode, get to a certain altitude, switch over to altitude hold mode. Then I'm going to input some roll and pitch maneuvers to make sure that the Arducopter can snap back from those maneuvers, because that's the exact type of maneuver that Autotune is going to be using. Here we go. Doesn't seem to be oscillating at all, which is good. Seems to be self-leveling fine. So we'll go ahead and set her down. Get ready for our auto-tune configuration.
Since we didn't have any significant oscillations during self-leveling, we're ready to go on to our auto-tune setup. We need to make sure that we've got a flight mode switch set up for altitude hold, which, as you saw earlier, we do. I went over how to set up flight modes in the first video of this playlist series. We're also going to need an auto-tune on-off switch.
Autotune activated.
I've got mine set up in Mission Planner as an auxiliary function using channel 10. To set up an auxiliary function on a channel, we go to our ArduPilot.org site, auxiliary function section, and we see the parameter we want is RCX underline option equals whatever feature we want from this long list. The X in RCX underline option is the channel number you'll be using. In our case, we'll be using channel 10, so our parameter we want to set is RC10 underline option equals 17. How do we make that happen? The same way we've been setting up most of our other parameters, through the full parameter list search bar. Now, of course, we also need to set up the switch in our transmitter, and you do that just like you would any other switch. Here you see my transmitter mixes page. Channel 10 is displayed as auto-tune. When I press to edit this channel, the next screen shows what I've filled in. I'm using switch D for my auto-tune switch, and I've set up a weight of -100 only because I want the channel high position of around 2000 in our radio calibration tab of Mission Planner to be when my transmitter switch D is in the forward or up position.
Autotune activated.
This next statement talks about a parameter we need to set for which axis we want to tune during a specific flight. Now we could attempt to do all 3 axes in one flight. My recommendation is not to attempt that unless you're capable of flying with a very large capacity battery. Each axis can take several minutes to auto-tune, so I do one axis at a time. The process is exactly the same for each axis, with the exception of changing this number for the parameter. If you set the parameter equal to 1, the Arducopter will twitch on the roll axis, which is a series of quick, short roll maneuvers. If you set it to 2, it'll twitch on the pitch axis, and so on. Since the Arducopter Autotune process is exactly the same for all 3, I'm only going to demonstrate one of the axes. For this video, I'll demonstrate the Autotune on the roll axis. So we'll go to our full parameter list and set Autotune axes equal to 1. And while we're there, we're going to ensure our Autotune aggressiveness parameter is set to 0.1. You could pick another option if you wanted to. Now that we've set up our parameters, let's take a quick look at the actual process we're going to do. First of all, the ArduPilot site says to perform the Autotune with little to no wind in a large open area. They really mean that. Let me tell you why. During the Autotune process, when your Arducopter is twitching, which are those series of short, quick maneuvers on each axis, it's going to drift. Every time you maneuver it with your sticks to keep it from drifting too far away, the Autotune stops. It will not restart until you let go of the sticks. If you're having to do this a lot because of wind, you won't be making any progress with your Autotune while your battery is running out of charge. I've actually gone so far as to schedule when I was going to do an Autotune based on the wind conditions by using a site called windy.com for my location. You just type in your zip code or the name of the town you're in, and it gives you the wind forecast down here below. Just plan on doing your Autotune with as little wind as possible in an open area. We're going to launch in either Acro or stabilized mode with our Autotune switch off. Then we'll go into altitude hold mode at a comfortable altitude. We'll flip the Autotune switch on and let go of the sticks. It'll start doing its thing, and you'll see progress messages on your goggle screen, or I suppose ground station if you're using one of those. When it's finished, it'll say success, and all you have to do to save the new PIDs for that axis is land and disarm. There's also a way to try them out before you save them, and I'll refer you to this link for further information on Autotune. During the Autotune process, remember you can maneuver the Arducopter to keep it within a specific area. When you do maneuver it, I'd recommend doing it as quickly as possible and then taking your hands off the sticks so it can start the Autotune back up while you still have battery life. Okay, let's go Autotune our roll axis PIDs.
Autotune activated.
Alright, that was a good Autotune session. The PIDs we had pre-Autotune are over here on the left, and the PIDs Autotune came up with are over here on the right. You can see Autotune changed the majority of the values in the first 3 columns of the first 2 rows. So now what? How do we know if these are any good? Well, I go fly with them in Acro mode myself, since my goal is to be able to fly Arducopter firmware in Acro mode while at the same time being able to leverage all of the other GPS-assisted modes whenever I want. So the question is then, are you happy with the Autotune after you go fly it? If the answer is yes, great, go fly. If your answer is no, not really, then we can tweak the Autotune PIDs manually using a few tools in Mission Planner. You can try the basic roll and pitch tuning with the slider if you'd like. It'll be sort of a trial and error method of moving the slider around and flying with the results to see if you like it. Or you can use the Mission Planner equivalent of Betaflight's Black Box Explorer. I'm going to show you the two tools I've used to dial in my final tune out of a lot that are available to you. First, you need to set up the ability to record your flight logs. My Maytech H743 mini flight controller uses an SD card to record the logs. Then you need to set the parameter log underline bit mask to record the values you want through the full parameter list search bar. These are the values I've selected. Of note, selecting attitude fast logs your Arducopter positional data on all three axes at the high rate of 400 Hz as opposed to a lower rate. Then after my flight, I grab the log off my SD card and save it to my computer. Let me show you how easy it is to use the Dataflash log as a tool to help you improve your Arducopter tune. Open up Mission Planner. You don't even need the Arducopter connected to the computer. Go to your Data tab and scroll over to and click on Dataflash logs. Then click on Review a log. Grab the log from your flight which you've saved to your computer, and I'm using the flight log from our Arducopter in this video immediately after its Autotune. Click on ATT, which stands for attitude, desired roll, and roll, which is your actual roll. It'll bring up their graphs for each in a different color. The desired and actual graph lines should closely match or overlay one on top of the other. If they're off by a couple degrees, that's usually okay, unless you want to get them absolutely perfect. Going back to the basic PID controller diagram on our chart, if your actual roll, shown here in green, consistently fails to climb up to meet the desired roll graph line in red, then you may want to increase your P gain by 5 to 10% from what it is currently, or lower your D gain by that same amount. What's important is the ratio of your P gain over that of your D gain, or your P to D ratio. So to correct this type of error, you'd want to increase that P to D ratio. On the other hand, if your actual roll graph consistently exceeds your desired roll at its peaks, you may want to do exactly the opposite. That is, lower your P to D ratio by lowering your P gain or increasing your D gain by 5 to 10%. This is the case on our roll axis. These overshoots are also really apparent in flight as sudden, severe, uncontrolled dips in the direction of the commanded roll. So I'm going to lower our P to D ratio to get our actual roll more closely aligned with our desired roll. After you make your changes, go fly, record the flight log, and review it again to see if you've made progress. Continue this process until you're happy with your results. You can do the same process for your desired versus actual pitch and desired versus actual yaw. Your goal is to get the desired versus actual graph lines overlaying one on top of each other as closely as possible. I'm going to show you one more thing before I reveal my final PIDs and take her out for a final flight. Arducopter has three main filters I'm aware of. The Extended Kalman filter, or EKF, and you can read up on that by going to this link. The Arducopter firmware also has a dynamic notch filter that you could read up on at this link. I've got my dynamic notch filter settings to 1, 1, and 3 for ESC telemetry based. Since I'm running bidirectional D-Shot firmware on my H743 mini flight controller, I've also got this parameter, servo BLH BD mask equals 15, coinciding with the first 4 channels, which are the control signal channels. The third filter is the static notch filter, and I'll get to that here shortly. Earlier, I enabled the dynamic notch filter, and you see that on the images of both the pre-Autotune and Autotune PIDs. I set its lower frequency limit to 123 Hz. Now I'm going to show you how I came up with that, and also how you can set up that static notch filter. Go back to Mission Planner, Data tab, and press Ctrl F on your keyboard. Press this FFT button, click on IMU batch sample, and load your flight log you saved to your computer. It'll bring up 2 graphs. One is for your accelerometer, and the other is for your gyro. I'm just going to go over the gyro graph for you. Here's what it looked like before filtering. You see I've got peak noise from the motors at about 246 Hz. I want my dynamic harmonic notch filter to take care of that. The Arducopter site recommends setting your lower limit frequency to half your peak noise frequency. So half of 246 is 123. That's the dynamic notch frequency that I've set, with a bandwidth of half of that, or 62. Now, after you've set the dynamic notch filter and recorded a post-filter flight Dataflash log, you can view the results of the dynamic notch filter. Here you see it's working really well on the motor peak noise we used to have around 246 Hz. It's gone. Now you do see another little noise peak or two to the right at about 333 or 368 Hz. Looking at our vertical scale, it's really not that bad, and we could let it go. However, for demonstration purposes, I want to knock that out with a static notch filter. So we'll set the static notch filter center frequency to that peak frequency. We go to our extended tuning tab, enable the static notch, plug in the center frequency, make the bandwidth about 100, and the attenuation about 30 dB. Write your setup. Now you know how to manually adjust both your PIDs and filters using ArduPilot Mission Planner along with your Dataflash logs. Here are the final PIDs I'll be using for this upcoming flight after going through this process myself. I'll continue to refine them over time, but these are pretty good right now. Let's see how they work. It's fly time.
Position hold coming up. Looking good. How about return to home? That's what I'm talking about.
That's going to do it for today. Hope you found this useful. Thanks for your time, and I'll catch you next video. Clear skies, friend.
Oh yeah. Sweet.